Real pleasure to be here, and it's a very energetic meeting. So before we talk about bees, let's talk about robots. It's been the dream of humanity for the best part of 100 years to create robots every bit as capable as ourselves, to live and work alongside us, to interact with us. And now with the advent of GPTs, it looks like we're kind of on the cusp maybe of even realizing that, with humanoid robotics, with transformers leading to these amazing advances in robotic ability. But I'm going to be provocative at an AI conference. And I'm going to point out that not everything functions perfectly. And of course, you always get gag reels from robots. But things in robotics can go badly wrong pretty quickly in a way that a human would seldom do. Now, why is that? Arguably, this is an unconstrained environment. This is a hard environment to solve in robotics. But even in much more constrained environments, such as driverless cars, you can have serious problems, even when it's just driverless cars interacting with each other and you've taken humans out of the loop completely, as in this Waymo car park in San Francisco, where you have Waymo gridlock. Now, let's reflect for a minute about the cost it's taken. These kind of projects like driverless cars are often described as moonshots. But let's think about the cost of a real moonshot. Now, Gartner estimates that the total private investment in driverless cars to date is on the order of $100 billion US. Consider the entire cost of the Apollo moon landing program. In inflation-adjusted dollars, about $250 billion. So in other words, we've spent just over a third of the cost of a genuine moonshot, of getting humans to walk on the moon, to reproduce the skill level that a human can attain with about 20 hours of training. And the cost of doing this is the construction and the energetic resources required and other resources required of gigantic data centers, leading to huge amounts of CO2 emissions, with, of course, corresponding consequences. So are we doing things the right way? I would argue there's a different way of doing things. And at my university spin-out Opteran, what we did was actually went back to very simple brains and decided to look at them in much more detail and look at how they truly function. And for comparison, the brain of a fruit fly, for example, the wiring diagram of the fruit fly was first announced last year. This is the first complete wiring diagram of any brain on the planet. It has only 100,000 neurons. Compare that with hundreds of billions of parameters, or even now trillions of parameters, likely in the case of GPT-5, for the use of transformers and deep networks. And you can see as well that this isn't just like a standard neural network, like a big soup where all the neurons are the same. There's a tremendous amount of structure in here that we can learn from. For transformers, in order to be able to get the kind of high levels of performance we're seeing with robot dexterity, with humanoids, etc., actually a fundamental problem is that unlike the internet, where you can simply collect data, scrape the data, as we were hearing on the last panel, you actually need to generate that data or collect it somehow from real robots. Now, that's very costly, so the proposal now is to actually use, again, supercomputers to generate those data synthetically in simulation environments, AI gyms like NVIDIA Omniverse here and NVIDIA Isaac. Okay, so maybe that's the solution to the problem. Maybe that's how we can solve getting human-level or even sophisticated animal-level autonomy. Well, consider how much simulation is possible to do, even with the largest supercomputers in the world, even as we invest trillions, potentially, in data centers internationally. And consider what those data centers are competing against. They're competing against 600 million years of evolution in a planetary scale, physically 100% physics-based simulator called Planet Earth, with a massive, massive parallelism. It's actually impossible, of course, to reproduce that level of evolutionary search. So instead, what we do is look at the brains that are produced by that evolutionary search. And using the latest techniques, such as putting animals in virtual reality, using the latest optogenetic techniques with which you can construct brain atlases of the kind I already saw. And here we see a particular circuit in the fruit fly, the ellipsoid body, which actually functions as a neural visual compass. It tracks the animal's heading in space. And you can see it's exquisitely refined and efficient and highly structured. And we can combine these techniques, the animal behavior experiments, the neuroscientific experiments, the brain atlases, the brain maps, to build faithful computational models. Here's a model of the ring attractor results from Janelia. That's actually reproducing those same experiments that were reported 10 years ago, but in a very faithful computational simulation. And of course, it's pretty easy to see that you could put that in a robot and use it to give it a sense of direction, which could be very useful. But actually, you can even apply these kind of models in much simpler ways. For example, colleagues at the University of Manchester took the ring attractor model and put it into classic deep reinforcement learning to improve the performance by about 50% on classic Atari and, in this case, Nintendo video game benchmarks, which has obviously been a long-standing benchmark to train and test algorithms against. But video games are, of course, they are worlds. They require world models in some sense to solve for AI, but they are highly abstract and highly simplified. Go back to the robots, the dreams of robots that humanity has had for so long. If we want them to truly work alongside us, they need to work in the environments we inhabit, environments with tremendous complexity, that we function in effortlessly. So, how can we do this? As I was saying, we should draw inspiration from biology. And we already do that. The actual inspiration we draw, though, should not be, for example, event-based cameras, which are inspired by the human retina, but a more systemic understanding of how the whole brain and the whole body function in tandem and evolved in tandem to solve the autonomy problem. So I'm going to give you 3 lessons drawn from evolution. The first is taken from the humble tunicate or sea squirt, and that is brains evolved first to solve movement. This is best demonstrated by the sea squirt, which has 2 life stages. In one, it's moving around, trying to find somewhere to settle down. And then once it settles down, it's never going to move again during its life, at which point it digests its own brain. If that doesn't clearly indicate to you that the value of the brain is for movement and nothing else, then I'm not sure what else could convince you. Next, stabilize your perceptual input. This is a beautiful example of a bird in this case. This is not a bee, just in case you're not a biologist like me. This bird of prey is fixating on a prey item on the ground, and you can see its head basically is locked in 3D space, and its body seems to move around it. It's actually doing a very complex inverse kinematics problem. So it's moving the body in order to stabilize the brain in space. There are other perceptual stabilization tricks. For example, your perception of color is actually not anything like the way a computer perceives color. It's informed by a world model of what you're looking at. Insects do something very similar as well, stabilizing their visual perception, and we'll see an example of that in a second. My final lesson is don't passively absorb information like most AI approaches nowadays do. Instead, real brains actively sample the world. For example, your visual system is not 2 high-definition cameras passively absorbing everything. Instead, it's actively moving a small, high-resolution area of your visual field around in an active sampling way, looking at faces, looking at the doors as they open, constructing a view of reality in a very active and constructive manner. So, transformers for robotics are often, and more generally, are often described now as foundation models. But I would argue it's actually these lessons that give us the true foundations. They give us the scaffold that evolution has built higher order brain function on top of. So our AI for robotics should function similarly. Start with solving the simple problems first, and then build progressively more and more complexity on top. And actually, my university spin-out Opteran has been doing precisely this. So I'm going to ask you to listen for 1 minute and watch for 1 minute. I couldn't bring all the variety of robots that Opteran's technology can function with onto the stage in the time available. So instead, I'll just invite you to see some of what we can do. So you can see Opteran is taking the lessons from the 10, 15 years of basic research I've led across multiple universities and now deploying it in the real world. And it's fitting to be giving this talk in Munich because our first public partnership and customer was announced this time last year, and it's with SafeLog, a well-known warehouse robotics manufacturer based in Munich and supplier to automotive and other big organizations. Now, Opteran starts by selling a navigation product because evolution solves navigation first, and you can sell navigation for robots. But the prospect is actually to use that as the scaffold in the same way evolution did, to build more and more intelligence on top of these fundamental foundations. With the goal, eventually, we would say, of reaching not artificial general intelligence, which is a poorly defined concept, and actually arguably not something we should even pursue, but artificial general autonomy, which is measurable and economically useful. I'm going to conclude by saying perhaps we should, as a society, reconsider our allocation, our resource allocation. You've seen people like Sam Altman saying we should have 7 trillion for AI chips to run increasingly large LLMs and other GPTs. But how about if we took a fraction of those resources and actually properly resourced the scientists who are trying to truly understand how the brain works, like those building the brain atlases or conducting animal behavior research? How about if our next moonshot as a society was actually to truly unlock the secrets of the brain? Thank you.